So let us discuss about charge simulation method, which is used to estimate the potential distribution in the insulation, preferably air insulation. This method is a very simple method compared to finite element method or finite difference method. So as we know that when a molecule of a dielectric is placed in the electric field, their negative charges get separated from positive charges. That means the dielectric which does not contain any free charges gets polarized. During polarization, a cluster of charges with electric dipole moment is formed, and you can notice here that this dielectric is unpolarized, so the different molecules are orienting in a random direction. But when an external electric field is applied, then electric dipoles are created, and you can notice that these molecules orient in a specific direction. So this is a concept which is used in a charge simulation method. So any surface of dielectric can be replaced by these charges, or in other words, the dielectric material can be replaced by some kind of charges which are fictitious charges, because now the dielectric material is polarized and it behaves just like a conductor, and therefore an electric line of force originates from this dielectric material. You can notice that there are two plates of capacitor and there is electric field applied, and because of this field the molecules having positive and negative ions, they are separated, forming electric dipole, and all these molecules are oriented in a specific direction with respect to external field. So we can replace this dielectric which is present inside this capacitor by fictitious charges or by some charges representing this dielectric slab. So in charge simulation method, the idea is to replace the electric field setup in terms of fictitious charges or simulation charges. Say for example, if you consider this particular part of high voltage system, then you notice that there is insulation, and then inside this insulation there is electrode which is charged with very high voltage. So with very high voltage applied to the electrode inside this equipment, then electric field will set up inside this insulation as well as in the surrounding area. Similarly, there is a high voltage transmission line, and when this transmission line is charged, then electric field is set up in the neighborhood. So by using charge simulation method, it is possible to estimate the electrical field intensity in the surrounding or electrical potential distribution. The idea is to replace this dielectric material in terms of fictitious charges or simulation charges. So basically there are three types of charges which can replace the entire dielectric material, which may be a solid dielectric material or which may be air which is acting as a dielectric medium. For example, let us consider this high voltage equipment, and this typical high voltage equipment has a spherical shape in this region, and this portion of this equipment is a straight. So this equipment can be represented in terms of fictitious discrete charges or simply simulation charges. So there are basically three types of charges used to represent or to simulate any high voltage equipment. The first type of charge is point charge. That means entire equipment can be replaced by point charges. Second type of charge is a ring charge. So if the shape of equipment is say ring type, for example this particular insulation has a ring type shape, then this insulation can be replaced by ring charge. Or here also you can notice that this spherical portion can be replaced by several rings with different diameters. There are 3 rings shown here representing the insulation in terms of these ring type charges. Sometimes it is convenient to replace the insulation by line charges. For example, this straight conductor representing transmission line can be represented by line charge, and then instead of considering several points along the transmission line, we can reduce the computations by replacing this entire line in terms of line charges of finite length. Similarly, there are few points we generally consider while applying charge simulation method. These points are called contour points and checkpoints. So we will see later on what is meant by say contour point and say checkpoint. So we conclude that the shape of individual fictitious charges or simulation charges can be chosen as point charge or line charge of finite length or ring or circular type of charge. So let us consider a small example to understand the basic principle of charge simulation method. So you can notice here there is a point say Ci and there are 3 charges in the surrounding. So let us consider this typical scheme where the large voltage exists, and you can notice that there are several conductors and there are several electrodes and insulations. So for this particular scheme we want to estimate the potential at a point representing Q1, Q2 and Q3 in the surrounding area. So what is done is we have to simply connect these points Q1, Q2 and Q3 with this point Ci, which is representing the point on the electrode where the electric potential is known to us. Let us assume that the distance R1 represents the distance between Q1 and Ci, and so is the case with R2 and R3. So the electric potential at point C can be written in terms of charges Q1, Q2 and Q3, which is written here. So phi I is a potential at point Ci, so it will be a summation of potential due to Q1, Q2 and Q3. So we can write this expression that Q1 upon 4 pi epsilon 0 R1, where R1 is a distance between the point Ci and the point Q1, and Q1 represents the charge at this point. Similarly, we can write other two terms. So we can represent this equation in simple form: Pi1 into Q1 plus Pi2 into Q2 plus Pi3 into Q3, where the term say Pi1 is equal to say 1 upon 4 pi epsilon 0 R1, and similarly I2 as well as Pi3. So these are the coefficients, and in these coefficients all the parameters are known because 4 pi is the constant and epsilon 0 is the permittivity of free space. Now if we consider two more points on the same insulation, we have point Cj somewhere here and there is a point say Ck. These points are also on the electrode. So it means that there are 3 points on the electrode which we have considered, say Ci, Cj and Ck. Then we will write similar expressions for point Cj and point Ck. So we will write similar expressions for the point Cj and Ck. Now let us connect these points Cj and Ck with these charges. Say this is connected to Q1, this is connected to Q2, and then this is connected to Q3. And we will also connect point Ck with all these three charges by straight line. Say here this is a distance between point Q1 and Ck. This is a distance between point Ck and Q3, and this is a distance between say Ck and Q2. So now we have 3 points where the potential is known to us. This is Ci, Cj and Ck, and we have 3 fictitious charges, namely Q1, Q2 or Q3, where we wish to estimate the electric potential. Remember, the point Ci, Cj and Ck, these are the points on the electrode and they are called contour points. So contour points are the points where the electric potential is known to us, and Q1, Q2 and Q3 are the points where we wish to estimate the electric potential. So we have already written equation for the point Ci, where the electric potential is assumed to be phi I, and it is written in terms of Q1, Q2, Q3 and R1, R2, R3. We can have 2 more equations for say point Cj and Ck, and if we assume that the potential at point Cj is say phi j, and then potential at point Ck is say phi k, so we can have phi j and phi k, and these equations can be written as p j1 q1 plus p j2 q2 plus p j3 q3. Similarly, we can write equation for phi k in terms of q1, q2 and q3, and then all these 3 equations can be written in matrix form. So this is done on the next slide. So this is all that we discussed earlier. Say for example, here we have got Qj with the number of charges, and let us consider any point Pi where the electric potential is Vi. The electric potential Vi can be written as summation of Pij into Qj, where j is equal to 1 to n. So there are n number of charges. So Pij is essentially a potential coefficient, and the voltage at any point can be expressed in terms of this expression q upon 4 pi epsilon a or epsilon 0 a. So this is a potential coefficient for a point charge. So if we have these fictitious charges expressed in terms of say line charges or ring charges, then we can write potential coefficients for these kind of charges as well. These potential coefficients depends upon the distance of the charges from the point under consideration, and this potential coefficient also depends on the permittivity of the medium. So it is very important to note that the number of contour points on the electrode surface should be same as number of charges in the insulating medium where the electric field intensity is to be estimated. So the set of equations which we obtained in our previous slide can be expressed in this matrix form. You can note that the square matrix represents a power coefficient matrix. The column matrix corresponds to the charges at different locations or fictitious charges, and the column corresponding to voltage represents the electric potential at contour points. Now since the contour points are located on electrode surface and the electric potential of the electrode is known to us, the voltage column is known to us. Since we know the permittivity of the medium in which the electrical potential distribution is to be found, and we also know the distance between the contour point and the point where the charge is located. So distance and permittivity, these two terms are known to us. Therefore, the square matrix representing potential coefficients is known to us. So by solving these equations, we can find these unknown values of fictitious charges. So once we get the magnitude of these fictitious charges, it is very important to confirm the magnitude of these charges. So now next, it is necessary to check whether the type and location of these charges as obtained in this step is correct or wrong. So in order to check the correctness of these charges, we need to consider few other points on the boundary of electrode where the potential is known to us. These points are called checkpoints. So checkpoints are the points on the electrode surface where the potential is known to us. And in order to confirm that the values of these fictitious charges calculated in the first step is correct, we have to consider checkpoints which are different from the contour points. Say for example, we have a checkpoint here which is say CC is one of the checkpoint, and we connect this checkpoint with these simulation charges by a straight line, and then we mark the distances like say R1 dash, R2 dash and R3 dash. So this CC represents the checkpoint, whereas CI represents the contour point. The potential at contour point is also known to us, and the potential at checkpoint is also known to us. So in first step, what we have done is we estimated the value of Q1, Q2 and Q3 by knowing the electric potential at Ci and other similar points like Cj and Ck. So in the next step, we consider three more checkpoints, say Cc1, then say this is Cc2 and this is Cc3, and we assume that the electric potential at Cc1, Cc2 and Cc3 is also known to us. So all these points, that is Cc1, Cc2 and Cc3, are again connected to these points, namely Q1, Q2 and Q3, and then we write similar equations. But in this case, now since we know the magnitude of the charges and we also know the values of these potential coefficients, because we know these distances, namely R1 dash, R2 dash and R3 dash, and similarly we also know the permittivity of this medium, which is same as before. So by knowing these potential coefficients, by knowing the magnitude of these charges, now we can calculate the potentials at Cc1, Cc2 and Cc3. And now we have two values of Cc1, Cc2 and Cc3. For example, Cc1, which is known, and we just calculated Cc from this equation. So now we have to write another expression, Cc1k minus Cc calculated, and we have to find whether it is equal to 0 or not. If this is not equal to 0, then we have to repeat these two steps. That means we have to rearrange these charges Q1, Q2 and Q3 with respect to Ci In that case, distances R1, R2 and R3 will change. Again we will find Q1, Q2 and Q3. Then again we will locate 3 points CC1, CC2 and CC3, and again we will calculate the values of CC1, CC2 and CC3 from the known values of Q1, Q2, Q3 and new potential coefficients, and again we will use this expression. So this is going to be an iterative process. These iterations are continued till this error becomes equal to 0. Once this difference becomes equal to 0, then we can say that the magnitude of Q1, Q2 and Q3 which is estimated is correct. So this is all about charge simulation method.